Alright, so today I'd like to talk to you about one of my favorite topics, which is nuclear magnetic resonance spectroscopy. We talked about this a little bit before when we talked about infrared spectroscopy. So in chemistry we call this NMR, and what we're specifically looking at in this chapter is proton NMR. So next semester we'll look at something called carbon-13 NMR. And if you recall from our discussion of infrared spectroscopy, we said in medicine these instruments are known as MRIs. And they're called MRIs because people were worried of the word nuclear. They thought it meant that there's uranium or plutonium or something radioactive that's involved in these machines. So it turns out that the phenomena of NMR occurs inside of the nucleus of the atom. All right, so it's a nuclear phenomena. It needs a magnetic field. It needs radio frequencies, and we need to see resonance occurring. Right, so let's talk about nuclear spin here. So it turns out that subatomic particles, like electrons, remember we talked about electrons, they can have spin up or they can have spin down, right, up or down. Protons and neutrons can be imagined as spinning on their axes also. Right, so they're rotating around. Now, in many atoms, such as, for example, carbon-12, the spins of the protons are paired against each other in such a way that the nucleus of the atom has no net spin. You can imagine if you have 12 protons and you get 6 spinning right in this up direction and then 6 spinning down, then the overall spin is 0. Okay? Now it turns out in some atoms, so this is what we're going to look at, right? We're going to look at proton NMR this semester and in carbon-13, and there's some other atoms that have NMR active nuclei. The nucleus does possess an overall spin that is either, and we'll just call this plus 1/2 or minus 1/2. So for the chemistry majors out there, if you go on and you take quantum, you'll learn that there's other spin states. You could have other numbers, but for us, we're going to look at plus 1/2 or minus 1/2. Now, here's the important thing. In the absence of an external magnetic field, like a strong magnetic field, the orientations are of equal energy. So in other words, like if you were to look up above, like here you have 6 up, 6 down, those would have the same overall energy in the absence of an external magnetic field. And when they have the same energy, in chemistry, we say that they are degenerate energy levels. However, if a magnetic field is applied, then the energy levels split. So let's take a look at that splitting process here. So here is our energy. Okay, we're going to call this our ground state. So our GS, and the energy of that is just going to be 0. Now, in the absence, right, remember in the absence of an external magnetic field, and we use the letter B to indicate magnetic field, the spins that are up and down are of equal energy. So they're equal energy. Right? So again, what we're going to do now is we're going to apply a magnetic field. So we're moving over here and we put a magnetic field. So that BO subscript O there means outside magnetic field. So it turns out that NMRs require very strong magnetic fields. So we have to use cooling liquids to get magnetic field strengths to be very, very strong. But in an applied magnetic field, then we see a splitting. So M plus 1/2 would be your lower energy, M minus 1/2 would be your higher energy. And so that delta E here is an energy difference, right, from the lower energy to the higher energy. And it's equal to HC, right, or H times this little weighted factor. This little variable up here depends on the atom that's being examined times the magnetic field. Now if we increase the external magnetic field, then the delta E will also increase. So what we want is we'd like to see a large delta E here so that we can observe the resonance phenomena occurring, right? So it turns out that down here below, let's talk a little bit about this in more detail. So down here below, that little thing here, it's a delta E. It's often very small, so you get both the M plus 1/2 and minus populated. If we increase the operational frequency, right, that's this, then we can increase the, delta E and get a larger population difference. So let's look at some energies down below. So it's 60 megahertz. Right? Your M, and this is something that you can calculate. I used to go through and do this years ago with students, but this is the end result, is that your M minus 1/2 is 10 million. And we're going to call that just N. And then the lower energy, plus 1/2, is 10 million and 9. So at that operational frequency, you have 9 extra protons in the M plus 1/2 energy state. That's not a lot, right? It's not a huge difference. Now, if you go up 10 times, right, up to 600 megahertz, then the upper energy level is N, and the bottom one is N plus 96. So you get 96 extra there. So that's nice, but still, it's a very sensitive technique, and we're not seeing a lot of protons move from a lower to a higher energy state. Now, the other thing that I wanted to point out here was this relationship between our frequency, right here, and our magnetic field. There's a direct relationship there. And so this is an important relationship that we're going to see a little bit later on when we talk about magnetic field strength and how it relates to frequency.